Hello, test, test. Hi, welcome to the Technical Director presentation. My name is Volker Helsle. I work for Filmakademie. I run this 30-month postgraduate course. And we have a packed presentation prepared from Denise, Paulo, and Daniel. It will be over 100 slides. So without further ado, we will jump right into the presentation. The only thing I would like to mention is that you can apply for the courses starting in fall and until May 15th. So if you have questions or if you're interested in studying Technical Director, please come see me, pick up one of these brochures here, and you can talk to me after that session. And let's welcome our Technical Director students.
Hello everybody, my name is Daniel and I'm going to start with this year's Technical Director presentations. I'm going to show you two of the diploma projects I've been working on as well as my own research project. To start off, just a bit of information about myself. Before coming to Filmakademie, I studied audiovisual media at the Stuttgart Media University, and then after graduating I worked at Machivision, a studio here in Stuttgart. Mainly doing compositing, but also some pipeline and tool development. And yeah, that finally got me interested in applying to study Technical Director. And so since 2017, I've been studying TD at the Animationsinstitut. And my main areas of interest are tool development and the fields of look dev, lighting, and comp. All right, the first project I'm going to show you is Evangeline. Evangeline is a diploma animation film at the Filmakademie, directed by Nadine Schwenk. It is around 7 minutes long and tells the story of this girl, Evangeline, who lives in the swamps with her father. And one day, Evangeline finds an alligator egg and she decides to keep it and raise the alligator by herself. And my main tasks on this project were look development, lighting, and compositing. And besides that, I also created some tools that help us with our workflows in these areas. In the beginning of the project, I worked a lot on character shading. I received fantastic textures by Elias, our main texturing artist, and we did a number of lighting and close-up tests with several shading iterations, and that was cool because there's a large number of close-ups and detail shots in the film, and so we had to make sure the shading detail can hold up in these shots, some of which you can see here on the side. And we also began early on in the process with some lighting and look tests. Yeah, this way we were able to make many iterations of some of the key shots of the film in order to create the look and mood we wanted to achieve. And this is an example of one of those key shots. And starting from the concept art in the upper left corner, we started shaping the look. And in the very beginning, we started working with previous assets, previous characters. And then we did several iterations and finally ended up with the somewhat final lighting and comp in the lower right. And yeah, here you can see an overview of a few shots from our current state of Evangeline. I'm currently still working on lighting and compositing together with Caro Kiesling. And we will finish the project by the end of July. And so hopefully next year at FMX we'll be able to present the finished project. Besides working on the visuals, I also developed some tools to improve and speed up our workflows. There are several tools for shading, lighting, and rendering inside this shelf in Maya, which is our production tool. And these tools are used to automate and speed up many of our tasks, like setting up render settings, creating custom light AOVs, or they can also be used to quickly change the characters' clothing colors and the level of dirt on their skin without having to go into the materials. And also part of this shelf is a number of tools for our Arnold operator workflows. For Evangeline, we are using the Scarif pipeline created by Lucas and Tim. There are two other TDs that will also present Scarif in a later talk today. And the diagram on the right visualizes how we bring animation into the lighting scenes using Alembic caches and Maya's GPU cache nodes. And to reassign the materials onto these caches, we are using Arnold operators. And there's some tools in this shelf that help with setting up the operators, exporting them, and then finally getting them set up in the lighting scene where they are used to reassign the materials. And besides the Maya tools, I created some Nuke tools to speed up our compositing tasks. The biggest one of them is this tool Bayou, which is a matte painting tool I developed that helps the compositing artist to quickly set up background matte paintings. And we use it mainly for the many exterior shots in the swamps, 2 of which you can see here on the slide. And the bottom example is from another diploma project called Pampas Paradise, where it was also used. And yeah, the matte painting is created by scattering input images on cards inside the camera frustum. And yeah, there's a lot of customizable attributes to quickly change the look to something you like. This is a quick demonstration of the tool in action. So as you can see, all you need is to input the shot camera and then give it an input image folder. And then you can adjust the tree size, the number of trees, and the distance from the camera. And then the tool scatters the trees inside the frustum. And yeah, you can use the random position seed and the random input seed to quickly iterate how this forest or the background matte painting will look like. And it's even better to do this in the 2D view so you can quickly see how the composition would look like. And then there's a couple of look adjustments like CD focus you can turn on and a haze for atmospheric effects. This is a quick example of how we use it in one of our shots. So you add it to the shot foreground. Usually you need some kind of grading for the trees to better match with the lighting of the shot. And then you can go into the tool and change the random seeds and create a background composition you like. And then this is a final look of the shot with the background matte painting. All right, this was a glimpse into the project Evangeline. Next, I'm going to talk about my research diploma project. Part of the TD studies is a scientific research and development project, which the TD students work on in their diploma year. And the goal of my research project is to implement Cryptomatte for game engines, or more specifically inside of Unity. Cryptomatte is an open source solution for automatically creating ID mattes at render time. It was originally developed by Jonah Friedman and Andy Jones at PsyOp, and over the last couple of years it has become sort of industry standard for creating object IDs. And it is available in most renderers and DCCs. However, there's not yet an implementation for game engines like Unity. Yeah, on the right side you can see an example of a production rendering with the object IDs created by Cryptomatte. And my motivation why I chose the subject for my project, I'm coming more from a traditional offline rendering and comp background, and I would love to adopt the possibility to work in real time and still remain the creative freedom and control of a traditional compositing workflow. And yeah, I would love to see how far you can push the images from a real-time engine if you have the right render outputs, like for example the ID mattes. And finally, there's more and more projects at Filmakademie that are starting to use real-time renderings for their film productions, and I'm hoping to use the results of my research in one of next year's diploma films. Yeah, coming to first prototype of my research. This prototype is based on a simple custom scriptable render pipeline in Unity. And it is able to output a first very basic version of Cryptomattes. On the right side, you can see the results of the prototype, the beauty rendering, and the Cryptomatte previews of object material and asset ID mattes. And on the left side, you can see a diagram of how this prototype works. The main part of the prototype is a game object with an attached script. And this script gathers all the names of the objects, materials, and assets in the scene. It hashes all those names using a Python implementation of murmurhash3, and then it exports the so-called manifest. The manifest is basically a dictionary with a names to hash ID mapping, and then finally the game object can be used to switch between displaying the beauty rendering, the regular rendering, and the material, the Cryptomatte hash values. Yeah, this is a quick demonstration of the tool. So you have, as you can see, it's just a scene with a bunch of spheres in some groups. You add the Cryptomatte manager game object. It needs a render folder and a render name. And then once you push this button, every object in the scene, the names are hashed, and the manifest is created, and it's stored inside the rendering folder. And on every object in the scene, a script is created which holds the hash ID of its object name, its asset name, and its material name. And now we can use the Cryptomatte game object to switch between displaying the regular rendering and the Cryptomatte hash values. And by switching between them, one after each other, we can render these images to file as EXRs. And once all of them are rendered out, we can take them into Nuke for compositing. We only need to input the beauty rendering. I built a small prototype relinker tool that automatically copies the Cryptomatte renderings into the correct channels and also adjusts the metadata. So this now works with the regular Nuke Cryptomatte gizmo. And as you can see here, we now have for assets, materials, and objects the IDs, and we can pick them. So this was the first prototype. After finishing this, I started working on adjusting it so it would work with Unity's high-definition render pipeline. So in the second prototype, when rendering, the Cryptomatte manager turns off all post-processing effects, switches all shaders to a custom unlit shader, and this once again sets the correct hash ID values using the material property block. This looks like that. So this is, for everyone who've seen this before, this is Unity's test or example scene for high-definition render pipeline. I just added an alembic. And now, first of all, rendering the beauty. For rendering, we use the offline render plugin from the asset store. This renders the whole sequence to EXRs. And then once this is done, we can use the game object to switch to one of the Cryptomattes and render this out, and then it switches the material to the hash IDs. And once everything is rendered out, we can take the sequence into Nuke again. And as you can see here, this is the entire sequence. And once it has been relinked, this can once again be used with the Cryptomatte gizmo. And so you can pick anything from the asset, material, or object IDs. For example, her head here, and the created mask can be used for anything like basic color correction in the scene. And so this is the finished, the entire sequence with some compositing done by using the Cryptomatte out of Unity. All right, the next steps for my research project are automizing this rendering process as far as possible. So as you have seen, you currently still have to render several times to get the beauty and the Cryptomattes out of there. In the end, I want to have a single render process and end up with a working multi-channel EXR. And then besides that, there's still a lot of things I haven't started working on yet. So this, in the prototype, was only a very basic version of Cryptomatte. And in the end, I also want to support other features like several objects sharing one pixel by using several ID coverage pairs. And finally, I also want to write the metadata directly into the header of the EXRs instead of having an external JSON file. The final project I'm going to show you today is the diploma project Strands of Mind. Strands of Mind is a virtual reality music video by Adrian Meyer. And for this project, I've been setting up a 360-degree virtual reality comp pipeline and also some editing and review tools. The core of our pipeline consists of a number of custom gizmos. There are custom read and write nodes, stereo utilities, and also a number of custom VR effects tools. And besides those, I also set up some workflow tools that make working with the VR content easier. One of those workflows is, for example, an automatic conversion, video conversion using FFmpeg that can be triggered by our custom write node after a render is done. And one of the tools we've been using most while working with VR content in Nuke is this small preview tool you can see on the lower right. It enables you to quickly switch between working in Nuke's regular view and two preview options. One of the preview options is outputting it to a VR headset, and the other one is giving you a rectilinear preview, which is visually similar to what you would see in the VR headset. Yeah, besides the Nuke pipeline, I also set up some tools for previewing VR content in general. One issue we were facing was that Houdini currently does not have any way of outputting images to a VR headset. And so we created some workarounds. One workflow we created early on during Previs is an automatic conversion from Houdini's OGL renderings that come out as cube maps to lat-long images in Nuke, and then a final video conversion using FFmpeg, so the Previs could be viewed in any VR player. And then when we switched over to our production renderer Redshift, we created a workflow to quickly see those renderings, once again using Nuke as a bridge for outputting. And yeah, we set up Houdini's IPR renderer so that it saves the current state of the rendering to file in a fixed time interval. And then in Nuke, I extended our custom read node to include an auto reload function. And this utilizes a Python watchdog process that monitors the rendering directory. And so every time the rendering is overridden, Nuke reloads the read node and sends the right rendering to the headset. And so this way, the artist can stay in Houdini and work there and just have Nuke open in the background for outputting the renderings to the headset. And then another thing we needed was some custom VR effects tools, because some of the regular Nuke nodes wouldn't work with lat-long images. They had problems around the poles, or they wouldn't work properly in stereo. And so I set up some custom effects tools for things like glow effects or distortion. And a lot of these effects are just based on Nuke's regular nodes or some gizmos we found on Nukepedia. And they were adjusted for our needs in a lat-long stereo environment. And in these images, you can see some of these effects in action in our test scene, the black hole sequence. And we actually used this test scene quite a lot because the black hole shot was the first production shot that was set up. And so it served kind of as our test shot and sandbox for developing the pipeline. And it was quite nice for that because it was a tricky shot. It's around 6,000 frames long in stereo 4K. So this is just the very beginning and the very end of the shot. And there's lots of action, as you can see, around the pole of the lat-long image. And it needs some heavy glows and so on. And so this has been ideal for us to set up and test all of our tools. All right, this is it for my presentation. Thank you very much. And next up is Denise.
So, hello, my name is Denise. I'm also a technical directing student at the Filmakademie. My presentation will be divided in 3 parts. First, I come to my R&D diploma project next year, which is based on the fast and deep deformation approximations paper. Then I will talk about the rigging system I'm working on for a short film named Bunter, Hund. And finally, I'll get to the shading R&D I am doing for the short film project Ernst Raabe. Before I start, something about me and my background. Before I came to the Filmakademie, I studied new media art at the Akademie Stuttgart, and my bachelor thesis was in interactive facial mocap application. I was a 3D and real-time intern at Pixomondo Stuttgart, and after my bachelor, I worked as 3D generalist at Mark 13 Stuttgart on the feature film Maya the Bee, The Honey Games. So, let me begin with my R&D diploma project. It's an open source extension of the research paper Fast and Deep Deformation Approximations. The paper was presented at the SIGGRAPH 2019 of the University of California and DreamWorks Animation. The goal of the paper is that complex production rigs can be animated in real time. And the rig deformations are approximated by a deep learning method. I want to examine the benefits and the drawbacks of the method in an actual short film production. So why would it be interesting to implement this paper? Talking about rig deformations, we usually have two options, quality or speed. On the one hand, we have film production rigs with high quality deformations, accounting, for example, bulges or wrinkles. They result in a slow evaluation time. And on the other hand, we have real-time rigs with a lesser quality because of a limited computational budget. Here we want to have the best of both worlds. We want to allow a better interactivity during animation, and we want to have complex deformations even in real-time applications. So why would we use neural networks for this? Using neural networks, you need a lot of time for the data generation and the computational heavy model training. The advantage is that the model training happens offline before the animation. During the animation, you just need to apply the learned data, which happens in real time with low computation costs. Neural networks are able to approximate arbitrary inputs and write out arbitrary outputs. In our case, it means they can approximate nonlinear deformations and write out nonlinear deformations, even their transitions. Neural networks are example-based. In our case, we use poses as examples. Here you can see in rough overview how the deformation approximation works, and after that I'll go into detail about the different parts. The mesh deformations of the input rig are split into linear and nonlinear portions. The nonlinear deformations are approximated by the deep learning method. For the final approximated mesh deformations, we need the original linear deformations, the skeleton transformations, and the new learned nonlinear deformations. So let me explain how we split the mesh deformations into linear and nonlinear portions. The nonlinear portion is computed directly from the joint transformations of the underlying skeleton, while each vertex is assigned to a single bone. In the lower part of the picture, you can see that it looks like a skin weighting, where every vertex has a weighting of 100%. In the upper part of the picture, you can see the target mesh, which is visibly different to the linear deformations. This residual represents the nonlinear portion, which is approximated by the deep learning method, what I already mentioned. And this leads me to my next point, the model training. The inputs for the model training are recorded at example poses. In the paper, they used about 10,000 example poses to approximate accurate deformations for an entire character. For each bone and its assigned vertices, we have the 3x3 rotation metrics and position for each bone as inputs, and the difference of the vertex positions between linear and nonlinear deformations, what I tried to illustrate in the lower part of the picture. So let's have a look at the deep learning method. We use a fully connected feed-forward neural network. You can see how such a network can look like. In the method, we use more neurons that you can see in the illustration. We have one neural network per joint, and each joint contributes 12 inputs to the neural network. We have 2 nonlinear hidden layers and 1 dense linear output layer. For the output layer, we have as much neurons as we have vertices in the input mesh times 3. The displacement of the vertices is parted in the x, y, z directions. Means for each vertex, we have 3 displacement vectors. To sum it up, we have an input movement and expect an output deformation. So much for the model training. We have also some drawbacks with the method. The method can't handle blend shapes that aren't joint-driven. Example for facial blend shapes that are controlled over sliders. It just considers bone-based rigs. The method computes the approximation per pose in the current frame only, means it can't handle dynamics because they're time dependent. Example for jiggle deformations or other secondaries. With this in mind, I did my first test implementations. Here you can see one considering blend shapes. The blend shapes are joint driven. On the left side, you see the target mesh, and on the right side, the output mesh with the applied deformer. We have a mesh size about 70 centimeter, and in red you see the error value of 4 millimeter. It represents the difference of the vertex positions between input and output mesh. The implementation is based on a test of Gustavo Bös. On his website, 3ddeeplearner.com, you can find a simplified implementation of the paper, considering one joint. It's done in Python 2.7 with a Keras framework with TensorFlow or Theano as backend. The data generation in Maya took about 440 minutes. I used 30 randomly generated poses, and the input mesh had about 2,000 vertices. The model training was done with Google Collaboratory, an open machine learning platform, and took about 20 seconds. The next implementation I tested was one considering dynamics. I wanted to see how far I could put the mentioned limitations in dynamics of the method. For the model training, I generated again 30 random poses, and I brought them to Houdini to simulate the wrinkles with vellum. On the left side, you can see how the input for the model training looks like back in Maya. On the right side, you see the rig with the applied deformer. You can animate it in real time, and you get a look of glove folds, but you haven't any secondary animation, what you normally get from a full glove simulation. So much for the test implementations. The method has, the last thing I have to say about my R&D project is to my current development state. At the moment, I try to transfer the existing test implementation to complex rigs with many joints. For that, I have to commit a joint map to the model training that contains data of each joint and its assigned vertices for every pose. And I have to split the vertices into subsets according to the bones they're influenced by. That's it for my R&D diploma project. And now I come to the short film projects I'm currently involved in. First, I want to talk about my rigging system I'm working on for a short film named Bunter, Hund. It's Colored Dog in English. The short film is about a world in black and white, where the government forces the people to remove every color. To my tasks for the project are the asset and shot handling and animation pipeline. It includes the look development. We evaluate to render in real time with Blender Eevee, and the hair grooming and simulation for the dog. I'm also responsible for the character rigs, what we will see now. For the project, I built a rigging system based on modules. A module can be an arm, a leg, or a spine, for example. The modules are connected over one input-output path. The advantage of that is that you can add, remove, or change character parts. I'm writing on my rigging tools in Python. The features of the rigging tools are custom constraints, a widget-based rig generation, and components for IKFK, spine, or ribbon. Here you can see the current state of the biped rig. It's a completely scalable character, and it includes stretchy and bendy limbs. I used the same modular rigging system for the background characters. Here you can see the face rig for the hero character. Challenging on this face rig were the blend shapes of the mouth, because it's basically just a straight line with no lips. I built a custom setup for the jaw movement, because the character has no chin. I animated a small sequence to show the range of motion of the current state of the face rig. Yeah, so much for Bunter Hund. The next thing I want to talk about is the shading R&D for the project Ernst Raabe. Ernst Raabe is the name of the hero character in the film. The short film will be about a postcard world. We will have different styles for different postcards, and it will be a mixture of 2D and 3D. To my task for the project include the character rigging of the hero character and the look development with custom toon shaders in Houdini. The 3D character will have a 2D look. To explain how the toon shader works, I rendered out the single shader masks. The base of the shader is a principal shader. I used the luminance of it to drive the gradients of the toon shader. Like that, it can react to any lighting condition. I've refit the luminance of the base shader to get hard transitions. And these transitions are used for the color mask that you can see in the upper part of the picture. We have 2 color shades for the diffuse mask and 1 color shade for the specular mask. In the lower part of the picture, you can see the inline mask, which is done over normals in camera space. The normals are sharpened to get more inner lines, and the outline mask that is done over an inverse hull mesh. Mixing these masks looks like this. First, we have the 2 color shades for the diffuse mask, the specular mask, the inline mask, and the outline mask on top. This is a usual setup for cell shading, like in other DCC applications too, maybe except for the inline mask. Based on this setup, I tried to generate 3 variations of the shader to test how you can play with the 2D versus 3D look. Here you can see how it looks like when the gradient masks have a smooth fall off. You can blend in again the original 3D look while maintaining the 2D feeling with the lines. Here I tried to mimic a halftone effect. I filled the gradients with dots that vary in size. The dots stick to the mesh, even if you would deform the mesh, because they're rendered in UV space. Because of this, it looks like they're part of the texture and not like in 2D post effect. With this last variation, I tried to get a sketchbook effect. I tested a cross-hatching for the gradients with randomized line thickness. The lines are rendered in rest space, so they stick to the mesh even if you would deform it. This wouldn't work in UV space, because then you would get disconnected lines around the UV island borders, and it would be harder to control the direction of the strokes. Well, that brings me to the end of my presentation. I hope you gained some insights to the TED studies. Of course, you can contact me via email or visit my website if you're further interested in my work. And with that, I will pass you over to Paulo.
Thank you. Hello. So, my name is Paulo Scatena. I'm going to talk a little bit about my experience with virtual production for a Filmakademie project, my research with light painting, and some motion capture locomotion library.
Traditionally, Animationsinstitut takes one foreigner as TD per year, so I'm here filling up the quota. I'm from Brazil, a town called Cuiabá, which is known only for being hot, and I'm not a big fan of heat, so I moved to São Paulo, graduated as an engineer, and kind of gave up on that path, went into animation, and kind of by chance started working with motion capture and performance capture in a small studio. And at first I was approached because they needed an animator, but what they actually needed, I would learn, is called a technical director, which is this person between the arts and technology, which is connecting the dots. It's kind of a artsy problem solver. And that was what brought me to Animationsinstitut, to strengthen this mindset of being resourceful and able to tackle different challenges. And my journey here began with Cat Planets, which is one of these year trailers. Maybe some of you saw it. I hope you liked it. My involvement was mostly in the game that was presented last year here at FMX, which is an installation in which people interact with this universe with laser pointers. And it was interesting because my challenges went from actually prototyping a laser pointer to testing it out, like how to track lasers and things like that, until developing the visuals of the game and implementing it in a fluid and reliable way, which is a very good environment to learn new things and new ideas, kind of a sandbox within a couple of months. And with this kind of production-oriented mindset, I was approached a couple of months later by one VFX supervisor that wanted some help for a project quite ambitious, which would involve a lot of VFX, meaning basically shooting actors in front of green screen and replacing the background, and being very beginner-oriented. I'm talking about things like this. You have your actor in front of your green screen, and you choose the environment to place it, in this case, and finally you composite it together, and it's perfect. And of course, this takes a lot of time, especially because actors are more complex than potatoes. And we didn't have that much time, so what we went for a slightly different approach. We began actually with the set, which was physically built as miniatures, and then you grab your actor and you want to put them together. So what if you put just a screen behind the actor, and you pipe the images from you digitalize your set and you pipe it through the screen. So already it's beginning to look interesting. So you put your camera in there, it's nice. But if the camera moves, the whole thing would break. So you need to actually put camera tracking in there. And what happens in the end is you have the final image together, the actor in the background, without this post-processing step. So what we ended up using was Unity, the game engine, and NCAM, which is a technology for camera tracking. And with them together, we could generate the backgrounds in a responsive way to the camera position in real time. And yeah, that was pretty cool. So, but what the hell am I talking about? If you don't really grasp, I'm gonna bring in some pictures to illustrate. Basically, it's about matching the graphics to the camera movement in a way that you generate a feeling of perspective, to the illusion of depth. Or in a more practical way, using a screen, it's just like creating the illusion that there's something beyond the screen. And in our case, in a physical set, it was somewhat more like this. We had our set, and we have a screen. Actually, we had two of them. And we're piping through all this data with Unity and NCAM. And NCAM is actually this toy together with the camera that looks like Wall-E eyes. And that's responsible for all the tracking. And it was quite an interesting combination because with real-time visuals, we were super dynamic to test things out, test post-processing and color correction and variations. And with camera tracking, we were allowed to give the cinematographer a lot of freedom so he could do all these crazy moving shots. And basically what we're talking about is virtual production. And this is a term that is quite big right now, but what does it mean? For our case, it meant using digital tools to enable your team to work as if it was a regular live-action shooting. And why would you want that? Because you do not want your crew to have to learn a new system if they are already good at something. You basically have your set with all these professional people working just the way they are used to. And what you do is you just pick two people and make them go crazy figuring out how to make it all connected together. So it's me and Dennis is the VFX supervisor. Of course, it's quite challenging. But it was also a very fun experience and super flexible and dynamic, and it's a very different approach to VFX. And I just wanted to acknowledge the support of the VFX supervisor and our producer, Josie, in this project was pretty amazing. A little bit about results. They are quite nice when you compare what would happen if you take the background out. So it's quite easy to forget that the whole thing is actually a virtual environment. And as a little bit of footage, I'm going to present some raw material that we had. So this is without proper grading, but already you can feel this integration with light and the digital and the physical set that would be quite hard to do in post-production. And to blend it in a believable way in camera was quite an achievement. For that, we also employed some tools, including the R&D internally developed tool VPAD. It's a virtual production tool set that enabled us to place lights and assets in a very flexible, real-time way. And I also developed a huge, giant remote control system based on TouchOSC for the VFX supervisor to play with settings on the flight. And this is kind of what it looked like. So you can tweak lights and conditions on the go. And we also had a huge green screen button, because for some cases, actually having a projector in your physical set represents a pretty good option to have the most perfect uniform green screen ever. So yeah, enough for Love and 50 Megaton. I will now go into my research project, which I call Lightseed. It's about painting with light, and I came with that mostly inspired by the physical approaches to VFX that came from this project that I just presented. Also with some talks that I was having with some lighting TDs, and also some papers that were presenting the use of automation in creative applications. But what is it about? It's basically using, most of you probably are familiar with the concept of light painting, like moving a light source in a long exposure photograph. So you have this illusion of something being there made by light. And I was like, okay, but what if we could play with this, having physical lights in a way that is more reliable, so you can start to have kind of VFX for physical environments? Can you actually do that? I didn't know, so that's why I decided to go for this kind of research. I started with very rough tests like this one. So basically a very simple dot light moving around a stop motion animation. And I kind of liked that. It's like, it's interesting to see all these reflections and all this more physically feeling lights. I'm like, okay, so the next step could be maybe getting a robotic arm and couple it with light control. It turns out that it's not as easy to get a robotic arm as I thought it would be, so it's still on the work in progress. But meanwhile, I was doing synthetic data, for instance, just rendering data so I could process them, and also capturing some light information from camera. And I started to wonder if you could use this information to integrate into something that you can use in post. Like if you can process this information to do something afterwards. And it turns out that you can. So I was developing this mindset of light it in post. You have an object, so you can do this process of capturing light information, and you just generate the lighting afterwards. So if you're like, you have this image, and you're like, no, I would like some more dramatic background light. Yeah, sure, just do it in post. And it started to feel flexible, because if you can generate the light in whatever way you want, you can also animate the light. So I tried that too. And whoop. Oh no, no. Play, haha. Which kind of felt promising because of all these details that would be so hard to do in a maybe digital compositing way. And I was still not happy with just static objects, so like, okay, so what if we could also have stop motion with light animation? And this is the next clip that almost started playing, and it has sound. So yeah, I kind of like that. But some people might still be, I'm not into having lights in my foreground? Why would this be useful for me? So I was like, okay, so what if we can use the same idea for more animation-friendly pipelines? So in this case, I was using the same technology or the same idea to generate a responsive light for a CG character. So I'm going to play a short clip.
You're having a breakdown, a stress response. Your power is kicking in to save you. It created me. You did.
And you're British?
Like I said, I'm your rational mind.
And basically all the light response that you get was first captured and then put into this scene in a way that feels like integrate. I'm going to show a little background. So what I started with a physical set that from camera looks like this. And for this setup, I just do a capture of lots of light information. And you take that the light information and you keep it somewhere. And then you grab your CG asset and you pipe that into, so you generate some light passes of this character. So in the end, you can composite it together. And in my case, I also had this 2D poorly animated thing. And you put them all together and do a little touch of compositing. I'm not a compositing TD, but I started to like this. And this is where I kind of stand right now. I still feel like it's still in early stages of research, but I really like this hybrid approach to it. And yeah, and I'm gonna finish up my presentation like a bad talk show. Like everybody in the audience gets a gift. Hey, it's data, woo! To explain it, it's just I like motion capture. I think it's a nice tool. And now that it's being more accessible, there's a lot of data being generated. So I started thinking about, like, can I get into motion synthesis, which is basically using data to generate animation? And I was trying to see what's there and what people are doing with that. But the thing is, it's a mathematical model. You're grabbing data and trying to transform it into something usable. And the quality of data really matters. So I was like, okay, so let's see how good the data is out there. Yeah, turns out it's really bad data. And I have a background in physical theater and mime. And I was like, maybe I can do something about it. Maybe I can try something better. So I developed a little locomotion path, something that I would repeat over and over and over and over again with variations of locomotion. Basically recording lots of takes with different speeds or different pacings or different styles. And it started as something more of a personal test, kind of just something for me to try out with. But it turns out the amount of data was pretty big. And the amount of useful data was still reasonable. So it was an interesting resource for the ongoing project, SOS, which is a project including 9 companies and institutions, including Filmakademie, which made me an official tiny collaborator for a big research project, so yay for me. And the data is publicly available, so yay for you. So if anybody is into locomotion, motion synthesis or stuff like that, just you can take a picture of that and go and download this data. It's available for research and educational purposes. And I would love if I could get some feedback on what was useful and what sucks and how would you do it better, because I really believe that we can benefit from a more pragmatic approach to generating data, a more thoughtful and structured approach to it, instead of just having somebody running around, because who would do that? That's just stupid. So yeah, that wraps up from my side. I appreciate you bearing with me. I hope it was somewhat interesting, and I do hope you enjoy FMX. I'm always available for a chat, so if you have anything to ask, talk, just text me or say hi if you see me around. I think, yeah, that's it. Volker probably has some words.
Wow, that was very interesting. I think we have time for some short questions, if there are any in the audience. Yes.
I have a question for the first speaker. When you have stereoscopic, panoramic, pre-rendered VR, there were for us always problems with the stereo separation for zenith and nadir, so the poles. Because of course, if you are looking up, then you aren't just moving your eyes in parallel, and if you have any results that fixes those.
We haven't really addressed those issues. I mean, we've noticed them, of course, sure, but we haven't actually implemented anything to. So I'm sorry, no better news there.
More questions? Okay.
First of all, congratulations to your projects. They are all very amazing. And I've got a question to Denise, which is, you said to the fast and deep deformation approximation, and you only use 30 data sets for the neural network. Do you think it would become better if you used more?
I'm just doing test implementations with small meshes. For this, I'm using 30 example poses. I tested also more, but the evaluation, the results weren't better than with 30 poses.
All right. Thank you.
I think it depends on the character in the end.
Okay. Are you planning on continuing this project?
I try to develop it further so I can use it for an entire character.
Thank you.
So yeah, I think that's maybe important to mention that the scope of your work here is really to bring it into production and to test drive it with a full production rig. So this is more or less the beginning, right, Denise?
Yeah.
Yeah. Okay. More questions? So don't be shy. All right, so then this was the technical director presentation, part 1. But there will be another full hour of crazy technical director stuff right after this. So these are 4th-year students. They'll graduate in a year from now. But in the next hour, we'll see students that have graduated a month ago. And we'll see some interesting open source developments using Quill in VR, and actually a very interesting fractal toolkit. So stay here if you're interested, and let's thank the speakers one more time. Thanks.